Today we're doing number systems, and we're going to start out with what we are all used to using, and that's decimal. And as we know, we count downwards, in this case, through each of the numbers. And when we get to 9, in order to represent 10, we have to go over to the next column, because now that's saying I've got 1 unit of 10 and 0 units of 1. And then we're going to continue downwards. And we have now our number system for decimal running from 0 through a 20. Now, if you're wondering why I am using Excel for this, well, back when I was in college, I started college wanting to be a medical doctor, and I mastered the handwriting. And so, to minimize confusion about my handwriting, that's why I'm using Excel. Now, for binary, binary says that we are counting in powers of 2, and in hex, that says we're counting in powers of 16. So I'm going to start with binary, and I'm going to use 5 bits just so that we have enough. 0 is going to be 5 zeros. 1 is going to be 4 zeros and a 1. Now, if I add 1 plus 1, the rules of mathematics never change. I'm going to exceed what the base is for that particular number system, so therefore I'm going to put a 0 in the column I was in and put a 1 in the next column. That now says I've got 1 unit of 2 and 0 units of 1, and I'm going to keep counting. And now, when I add 1, again, I'm exceeding the base. So 1 plus 1 is 0 carry 1. 1 plus 1 is 0 carry 1. And I'm going to end up with this as representing 4, meaning I've got 1 unit of 2 squared. And I'm going to continue counting in this fashion. All the way down. Whoops. Whoops. So now if we take a look at 20, that is saying I've got 1 unit of 2 squared and 1 unit of 2 to the 4th, which is 16. 16 plus 4 becomes 20. Now for hex. Hex means I'm counting in base 16. Rules of mathematics never change. So I'm going to start counting. Whoops, now I get to 9. What am I going to do at this point? Well, I can't put 10 in a single column because each column represents a power of the base. So 9 plus 1 becomes A, and that's just the international standard. Everybody had to agree on something that would represent 10. Now we've got 11, 12, 13, 14, 15, and now when I get to 16, 16 is really 1 unit of 16 and 0 units of 1. And I'm going to continue counting. And this will proceed similarly. Now when I get, I'm going to do dot, 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 and I'm going to put 32 here. 32 is going to be 2 to the 5th plus 0, 2 to the 4th plus 0, 2 cubed, 0, 2 squared, 0 2s, and 0 1s. So that will represent 32. In base 16, 32 is 2 units of 16 and 0 units of 1. And this is what gives us our number system of decimal, binary, and hex. Let's do some binary to hex conversions. We're going to start simple. And let's just say somebody gives us 0, 1, 1. Now, the rule for the conversion is if it's in binary, the number of bits must be evenly divisible by 4. If it's not, you make it evenly divisible by 4, which means in this case here, we're going to need to pad this out to 0, 1, 1, and then our resulting hex, and until you get this down pat, you're going to have to go to the table, and what do I see for 0, 1, 1? Well, 0, 0, 1, 1 gives me a 3 in hex, so that's what I'm going to put. And I should have made this 0, 0, 1, 1. Okay, let's try another one. Let's try 1, 0, 1, 0. Now this is a evenly divisible by 4 number of bits. And now that means there's going to be no padding, and I'm going to go and take a look at the number system, and I have 1010, and that gives me an A as the conversion to hex. Now let's try something a little bit more difficult. Let's do 110001. Well, what I have to do is to break this into 2 groups of 4 bits. So the first thing I'm going to do is I'm going to take the 1 at the beginning and add 3 zeros, and then in the next column, I'm going to take 1, 0, 0, 1. So I've broken it into 2 units of 4 bits each. And now I'm going to take each of those 4 bits and convert it into hex. So 0, 0, 0, 1, well, this one's easy. That's going to be a 1. And then 1, 0, 0, 1 is going to be a 9. And you can check a number system yourself after we're done, because I'm going to be including this Excel spreadsheet. And 1001 is 9. Now, the only reason I know this is I've been doing computer science stuff since I was 15 years old, so this is all second nature. Let's try another one. Okay, so the first thing I'm going to do is I'm going to break it into counting from the right going to the left. I'm going to get 0, 0, 1, 1, and then the next group of 4, but there's only 3 bits, so I'm going to put 0, 1, 0, 1. And now I'm going to look at each of those, and I'm going to say, well, 0, 1, 0, 1 becomes a 5 in hex, and 0, 0, 1, 1 becomes a 3. And let's do one more. Okay. So the right, and I'm going to take those first 4 bits, and then the next one I don't need to pad because it is 4 bits, and I'm going to take a look at each of those 4 bits. 1, 0, 1, 1 is going to be a B for the first set and a B for the second set. And again, like I said, it's perfectly okay to use the first sheet from this Excel spreadsheet until over time it just becomes natural, and you'll be able to look at 4 bits and immediately convert to hex or to decimal. Now let's take a look at converting hex to binary. So starting off easy, we're just going to say B. And B becomes 1011. Now you're asking probably what happens if it was a 3. A 3 is going to become, and since 4 bits are required to do the conversion from binary to hex, when you convert from hex to binary, you're going to turn it back into 4 bits. So 3 becomes 0011. Now if we went to 2 digits, like A3, I'm going to take a look at each of these going from left to right, and I'm going to say, well, A is 10, A is 1010, and 3 is 0011. Let's try another. Let's do 6B. So, going from the left to right, I'm going to say 6 is 0110 in binary, and B is 1011. So now I've converted 6b to to binary. And let's try ABC. Well, the rules of mathematics never change. So therefore, ABC is going to be 1010 for the A. B is going to be 1011, and then C is going to be, what do you guess? Well, I say it's going to be 1100. And that is how we convert from binary to hex. Now, to convert binary to decimal, to convert binary back to decimal, I have a couple of columns here. And first column is going to be what number it is. The second column is write the bits out going from right to downwards, and we're writing the powers of 2. We're going to apply the bit value, which 1 is 0, times the power of 2 product, and we're going to sum everything up. So let's start out 0, 1, 1, 0. What we're going to do is we're going to write this from left going downwards as 0, 1, 1, 0. Then we're going to get the powers of 2. Well, the first power of 2 is a 1. Second power of 2 to the 0 is a 1. 2 to the first is a 2. 2 to the second is a 4. And 2 to the third is 8. The next step is we're going to product. 0 times 1 is 0. Times 2 is 2. 1 4 is 4. And 0 times 8 is 0. And I'm going to sum these up and get a 6 as the result. So 0, 1, 1, 0 becomes a 6. Let's try a little 1, 1. I'm going to put them vertically, going from right to left, and then I'm going to the powers of 2 to the 0 is 1, 2 to the first power is 2, second power is 4, third power is 8, fourth 16. Then I'm going to multiply everybody together. The first times 1 is 1 times 2 is 2. 0 times 4 is 0. 1 is 8. 1 times 16 is 16. Add this all up, I'm going to get a result of 7 because 16 plus 8 is 24, 2 is 26, and 1 is 20. We'll try one other one. We're going to write this vertically. And then we're going to write the powers of 2. 1, 2, 4, 8, 16, 32, 6, and 1, 8. Now I'm going to the bit times the power of 2, and 0 times 1 is 0. 1 times 2 is 1 times 4 is 4. 0 times 8 is 0. 1 times 6 is 16. 1 times 32 is 32. 0 times 64 is 0. And 1 times 100 is 128. This up, and I'm going to get 28 plus 32 is 160, 106, 180, 182. Okay. Three numbers here that are in decimal, and we're going to convert them to binary. The process to convert from decimal to binary is we're going to take the number 18 to start with, and we're going to divide it by 2. We're going to divide it by 2 and put the remainder in the column that says remainder. So 18 divided by 2 is 9, remainder 0. If the number that we're currently looking at, which is 9, is not 0, we're going to do the process again. 9 divided by 2 is 4, remainder 1. 4 is not 0, so we're going to do the process again. 4 divided by 2 is 2, remainder 0. 2 is not 0, so we're going to do the process again. 2 divided by 2 is 1, remainder 0. And 1 divided by 2 is 0 times 2, remainder 1. Now that I've got a 0, I'm going to read this backwards, and I'm going to get 0, 1, 0, 0, 1, 0. Normally we would pad this out to a multiple of 8 bits, but because we're just learning right now, I'm not going to do that. For 35, we're going to do the same process. 35 divided by 2 is 17, remainder 0. 17 divided by 2 is 8, remainder 0. 8 divided by 2 is 4, remainder 0. Whoops, that should have been a 1. Okay, 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0 times 2, remainder 1. Now that I have the 0, I'm going to read backwards, and I get 35 to be 0, 1, 0, 0, 0, 1, 0. Now, does anybody see the mistake that I made? Well, the mistake is 35 divided by 2 is 17, remainder 1. And that gives us the correct translation. How about with 138? 138. 138 divided by 2 is 69. Remainder 0. 69 divided by 2 is going to be 34, remainder 1. 34 divided by 2 is 17, remainder 0. 17 divided by 2 is 8, remainder 1. 8 divided by 2 is 4, remainder 0. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. And now I'm going to read this backwards, and I get what? Well, it's going to be 0, 1, 0, 0, 0, 1, 0, 1, 0. And that is the correct answer. Many people ask me, what happens if they give me a decimal, like for example 0.6? How do I convert that to a binary fraction? Well, what I'm going to do is I'm going to take the 0.6 and multiply it by 2, and I'm going to get 1.2. Now notice what I did. Anytime that I'm going to become greater than 1, I'm going to put the 1 over in the column, which we're just going to call overflow. And then I'm going to repeat this again. 0.2 times 2 is 0.4 with no overflow. 0.4 times 2 is 0.8 with no overflow. 0.8 times 2 is 1.6. And 0.6 times 2 is 0.2 with an overflow. 0.2 times 2 is 0.4 with no overflow. Now, here's an interesting problem that we've run into, in that this number will never convert to binary wholly, meaning this is a repeating binary fraction, and thus we have to essentially cut our losses. And what this is going to turn into in a binary fraction is 0.100110 if we cut off at this point. Now, how do we determine where we cut off? Well, the determination is based on the number of bits that we want or can actually represent, or whether it's something that easily converts. So like for example, let's do 0.75. 0.75 is going to easily convert. And what we're going to do is 0.75 times 2 is 1.5. 0.5 times 2 is 1 with a 0. Now, once I've got a 0, that means I'm done. And so the binary fraction would be 0.11. Now, the binary fractions are similar to the way that we do the binary numbers, excepting that we're going to be working with negative powers. So, how does this convert? Okay, and how does this convert back? Well, let's zoom this out. And we're going to take the one that we just did right here. And we're going to convert it back to a binary. We're going to convert it from a binary fraction to a decimal fraction. So what I'm going to do is, instead of starting from right to left, I'm going to start from left to right, omitting the 0. And here's a bit. And then this is power of 2. And let me center this. And so I'm going to have a 1. Well, this is the negative first power of 2. Then I've got a 0, a 0, a 1, and a 1, and a 0. And this would be the negative 2, negative 3, negative 4, negative 5, and this would be the negative 6. So the negative first power is a half, then it's going to be a quarter, and I'm going to convert my whole table here to be text so that we don't accidentally get the wrong thing. So the first one is going to be a half, then a quarter, then an eighth, then a 16th, then a 32nd, and then 1/64th. And so now this is going to be, same rule, 1 times a half is a half, then 1 times a quarter, 0 times a quarter is a 0, 0 times an eighth is a 0, 0 times a 16th is a 16th, 1 times a 32nd is a 32nd, and 0 times 64 is 1/64th is 0. Now I'm going to sum this up. Now in summing this up, some people will convert it to decimals and then just add up the decimals, but this is going to be 16 32nds. This is going to be 2 30-seconds and 1 30-second. So we get what? 16 plus 2 plus 1, that's going to be 19 30-seconds. But people these days do everything in numbers, and I mean decimal numbers. So I'm going to convert this back to a general, and I'm going to do the division. Excel and I are having a little bit of argument right now, so I'm going to force it to what I want. And then this is going to equal. And now when I sum this up, I'm going to get 0.59. So here's an interesting predicament, and this is common amongst all computers and calculators. A computer will never ever give you the correct answer unless you have something that in decimal that will directly convert to binary. It will always be off. So for example, we started out with what? 0.6, but the computer is going to store it as 0.59. That can be a real issue. And this issue is something you have to take note of as you go on in computer science, in that a computer is never accurate, which means dead on, but it is precise, meaning it's within the ballpark. So 0.59 is within the ballpark of 0.6, but it's not exactly 0.6. And as you keep doing math, the multiplications are going to essentially give you a bunch of errors, meaning you're not going to get exactly the correct answer, but it's going to be good enough. One thing that you have to be wary of also is that within a computer, you have a finite number of bits. Eventually, those bits cannot hold the value that you are trying to convert if it is too small, and the computer just represents it as 0 once the number gets to be too small. And what happens when you multiply by 0? You end up with a result of 0. One of the key things to remember is that a computer never is accurate. It is just precise. If there are any questions, please let me know, and I hope everybody's doing well.